The early 19th century faced a transportation crisis. Horse-drawn carriages and waterborne transport were inefficient for moving goods and people across vast distances. The Industrial Revolution demanded a faster, more reliable solution. This need fueled the invention of the steam locomotive. It emerged as a transformative technology. The locomotive promised to reshape the world. Prior to the locomotive, transporting raw materials and finished products was a slow and arduous process. Horses could only carry so much weight and required frequent rest. Waterways, while efficient for large loads, were limited by geography and weather conditions. The steam locomotive promised to overcome these limitations. It offered the potential for high-speed, all-weather transportation over land. The invention of the steam engine marked a pivotal moment in history. It harnessed the power of steam to generate mechanical energy. This invention paved the way for the locomotive. Early pioneers experimented with different designs. They sought to create a self-propelled vehicle capable of pulling heavy loads. These early locomotives, while rudimentary, demonstrated the potential of steam-powered transportation. The development of the steam locomotive was not without its challenges. Engineers and inventors continued to refine the design. At the heart of the 19th century locomotive resided the mighty steam engine. This ingenious contraption served as the driving force behind these iron horses, converting heat energy into mechanical work. The process began with the combustion of fuel, typically coal, within the locomotive's firebox. The burning coal generated intense heat, which radiated through the firebox walls into the surrounding water jacket. This water, heated to a boil, transformed into steam. Steam, being less dense than water, exerted pressure. The high-pressure steam was then directed into cylinders where it encountered pistons. These pistons moved back and forth as steam pushed against them. This reciprocating motion was the key to converting steam power into mechanical energy. The boiler stood as a testament to engineering ingenuity, its robust form housing the transformation of water into high-pressure steam, the lifeblood of the locomotive. Crafted from durable materials like steel or iron, the boiler was designed to withstand immense pressure and heat. Inside the boiler, a network of tubes carried water through the heart of the firebox. This design maximized the surface area exposed to the intense heat, facilitating rapid water heating and steam generation. The boiler's efficiency in generating high-pressure steam was crucial for the locomotive's performance. To ensure safe operation, boilers were equipped with an array of safety features. Pressure relief valves prevented catastrophic pressure buildup by venting excess steam. Water gauges allowed engineers to monitor water levels, ensuring the boiler tubes remained submerged and prevented overheating. Engineers incorporated innovations to enhance efficiency and steam production. Section 4. Valve gear, orchestrating the flow of power. While the boiler generated the steam, it was the valve gear that dictated its flow, acting as the control system for the locomotive's power. This intricate mechanism managed the entry and exit of steam into the cylinders, ensuring the smooth operation and direction of the engine. Precision and timing were critical in the valve gear's operation. By controlling when steam entered and left, the valve gear dictated the piston's motion and consequently the locomotive's speed and direction. This ingenious mechanism ensured the steam was used efficiently to generate maximum power. Different types of valve gears were developed throughout the 19th century, each with its own advantages and complexities. Some popular designs included the Stephenson valve gear, known for its simplicity and reliability, and the Walschaerts valve gear, favored for its efficiency and smoother operation at higher speeds. The selection of valve gear depended on the specific requirements of the locomotive and its intended use. Section 5. From piston to wheel, the art of translating reciprocating motion. The transformation of the piston's linear, reciprocating motion into the rotational motion of the wheels was a testament to the elegance of mechanical engineering. This crucial conversion was achieved through a series of ingeniously designed components, ensuring the power generated within the cylinders translated into the locomotive's movement. The connecting rod served as the critical link between the piston and the wheel. Attached to the piston at one end and the driving wheel's crank pin at the other, the connecting rod translated the piston's back and forth motion into a rotary force. As the piston moved, it pushed and pulled the connecting rod, which in turn rotated the driving wheel. The driving wheels, typically large in diameter, were key to the locomotive's traction and power. Larger wheels were better suited for higher speeds, while smaller wheels provided greater torque, essential for starting heavy loads. To ensure smooth power delivery and minimize wear and tear, the driving wheels were precisely balanced. Section 6. Taming the Iron Horse. Advancements in braking and control systems. As locomotives grew in size and speed, the need for reliable braking systems became paramount. Early braking systems were rudimentary, often relying on hand-operated brakes applied directly to the wheels. However, as train lengths and speeds increased, more robust and responsive braking solutions were needed. The invention of the Westinghouse air brake in the mid-19th century revolutionized train braking. This ingenious system utilized compressed air to apply brakes to all cars simultaneously. This innovation significantly improved braking performance, enhancing safety, and allowing for larger, faster trains. The air brake system consisted of an air compressor, a reservoir to store compressed air, and brake cylinders on each car. When the engineer applied the brakes, compressed air was released from the reservoir and directed to the brake cylinders, engaging the brakes throughout the train. Section 7. Strength on rails, chassis, suspension, and the weight of innovation. The chassis and suspension system of a 19th century locomotive were engineering marvels, designed to withstand the immense weight of the boiler, engine, fuel and water, while also navigating the often uneven and unforgiving rail lines of the time. The chassis provided the structural backbone of the locomotive, ensuring its integrity under immense stress. Early locomotive chassis were constructed from wood, but as technology advanced, iron and later steel became the materials of choice. These robust materials provided the necessary strength and durability to support the locomotive's ever-increasing weight and withstand the rigors of daily operation. The chassis had to be both strong and flexible. The suspension system played a crucial role in ensuring a smooth ride and preventing excessive wear and tear on both the locomotive and the tracks. Leaf springs, often made of layers of steel, were commonly used to absorb shocks and vibrations. These springs acted as cushions, dampening the impact of uneven track and allowing the locomotive to maintain contact with the rails.